Welcome. I'm an electronics hobbyist and technology content creator dedicated to breaking down embedded systems, circuit design, and microcontrollers. Imagine water flowing through a pipe. If the water pump pulses unevenly, the water stream will jerk and stutter. Now, imagine adding a storage tank with a flexible rubber barrier inside. When water pressure spikes, the tank absorbs the excess water and stretches. When pressure drops, the rubber snaps back, pushing water out to keep the flow completely steady. This is exactly what a capacitor does with electricity. It acts like a temporary power reservoir, absorbing voltage spikes and filling in voltage drops to keep your microcontrollers running smoothly without resetting. At the physical level, a capacitor consists of two conductive plates separated by an insulating layer called a dielectric. When a voltage is applied, electrons accumulate on one plate, creating an electrostatic field that pushes electrons away from the opposing plate. The capacity to store this charge, called capacitance, C, is determined by the physical geometry. The permittivity of the dielectric, epsilon, multiplied by the area of the plates, A, divided by the distance between them, D. C equals epsilon times A divided by D. The foundational relationship between charge, Q, capacitance, C, and voltage, V, is defined by Q equals C times V. Because a capacitor blocks direct current, DC, once fully charged, but allows alternating current, AC, to pass through, its dynamic behavior over time requires calculus to model. I of t equals C times dV dt. This derivative formula explains why capacitors are vital for filtering noise. Rapid voltage changes, dV dt, create high current paths, allowing high-frequency noise to pass safely to the ground while preserving the stable DC power line.